So welcome on the second modeling part in the ABAQUS, focusing on the cohesive surface traction. My name is Lukas, and I work as a computational validation engineering company Idea Statica, um, mostly oriented on the concrete and the steel structures. So maybe you will know me from the webinars because I'm in the close relationship every day with the customers. So maybe you also know me from the webinar sessions. Okay, that's I would say all from me. I have some maybe just to mention that I have some structural engineering and mechanical engineering background. So once some questions will come, I will be able to try to tackle it and answer. Today's content, I want to focus on the modeling, some linear damage evolution as an inbuilt feature in the ABAQUS. Also, I would like to define and introduce you how you can define user-defined evolution, and we will just compare the inbuilt and user-defined damage parameters. Also, we will touch a little bit the Python script where all the data are basically coming from. I mean the slip damage data that will be used for user-defined evolution or user-defined settings. And we will touch a little bit results interpretation because the like a deeper exploration of the results will be in the next session. So actually, let me just recall what we discussed last on the last session. So the goal is to like a model and validate the um, unconfined concrete, or basically the embedded bar inside the volume of the concrete, and the goal is to set the traction displacement law and basically receive the same response to have the first I would say initial assumption appropriately defined. So once I will just recall what failure modes you can come across if you are trying to pulling out the bars from the concrete. There can be some like a splitting or pull out. Actually, at this stage, we will focus on the splitting failure that is dominant once you have unconfined concrete. So there is like a brittle failure, and you're just reaching some peak, and after the peak, like a post-critical state is coming the damage. So this is our testing setup. Um, I just put inside some parameters that we will be using during the modeling. Some concrete will be C30/37 with the second modulus of the elasticity that is coming from this grade. Reinforcement bars B500B, and the traction separation law that is outlined on the right part of the screen. There is the T0, what is basically the area of the maximal peak traction shear stress. From this point on, there is some damage initiation, so also you need to have some relation to damage initiation slip, what is basically S0, and traction in the fracture is like a 10 millimeters. Yeah. Sorry, not the traction is equal to 0, but the slip at this fraction is equal to 10 millimeters. So from this point on, there is like a zero contribution of the stiffness, and there is just pulling out or moving away the bar from this volume without any traction. Actually, we need to just touch the results because we need some results as a field output from the ABAQUS. The first one is like a CDMG, what is the scalar damage variable that is related to um, this cohesive contact. Also, we will just turn on and select the damage initiation criteria that was mentioning in the previous presentation, but I will just mention it again. There can be some like a maximal stress, maximal separation, quadratic stress, and quadratic separation. Those are basically the options that you can select for your damage initiation criteria. Something about the Python script, because at first I just defined the traction separation or traction slip curve. Based on that, I just calculated the damage that will be used as a user-defined damage after we will try out the inbuilt function. And as I mentioned, the trend of the damage is hyperbolic, but the basically the linear evolution after the uh, post-critical behavior is basically linear. I mean the traction versus slip. So we will just I will just introduce you what data you need to put inside, and how the Python will help you to prepare the data. So this is the output, basically what you should receive from the ABAQUS. The outputs will be compared with the predefined data that we insert into the ABAQUS, and they need to matching. So we will just introduce the data and talk about more about the data. But at first, let me remind you that I've been just endorsed as a certified trainer of IDEA Statica. So once you have some project, or you wanted to consult something, do not hesitate and drop the email or drop the message into the struckinside@gmail.com. So I will respond to you soon. Um, I'm also quite active on the LinkedIn, so for more content, you can just follow me there. And as I mentioned, this is not the last session, because the third session will be um, focusing on the detailed results explanation plus post-processing in the Python, where you can just, based on the results, you can just compare it with your already used Python data, and have it everything in the one package. So I just already open up the Abacus, and I will approach and start with the part. The part that will be first modeled is the concrete. So I will just write here concrete. I will just select deformable and the solid. So you can just create a circle. The circle will have like coordinates at the origin 0, 0, and the radius will be 100 millimeters. So once you do it, you will just rescale it. You will receive the circle. I will just put here some dimension, confirm it, and I will extend it to 200 millimeters. So actually, I have a cylinder, and what's basically I need to do, I need to just drill out the opening there. So here is the option how to create a cut. So once I will select, yeah, okay, I will select the edge, and actually here in the same manner, I will create the circular opening that have coordinates 0, 0, 0, and the perimeter 10 millimeters. Actually, I will put here for sure the dimension to know that it's already what I want. And once I confirm it, uh, the Abacus will ask me if I wanted to drill it through or just blind. And as you can see, the direction has been created in this basically like opposite to the global direction. But my goal is to put there 100 millimeters. This is my direction, so I will just confirm it, and that's being drilled out properly according to my expectation. So once I have it, I will just create a plane and cut the circular or this cylinder volume into the four pieces to have it like a uniform mesh and structured mesh. Actually, here create the datum offset from a principal planes. Um, the first plane will be YZ. So once I do it, it's being created, and the second plane will be XY. Ouch, no. I will just, I can go to the feature, delete, I will select it and confirm it. So once I replicate the same operation, so it will be the X and the Z. So once I do it, actually I can just move here to create a partition via the datum plane. I will just select the plane, and one it's been I would say cut it, you need to always select which part will be basically cut. I will cut it in the same manner the bottom half of the cylinder. So that's been created and partitioned. So that's good. That's good, and I can proceed to rebar. So in the same manner, I will create the rebar. Uh, Once I will create it, the origin will be in the coordinates 0, 0, and the radius 10 millimeters. So once I have it, I will just put dimension. Once I confirm that, I can just move to extrude about the 200 millimeters and create a bar. So once the bar is created, I will create in the same manner the cut in the four planes. So it will be like a XY and not a XY. This you can see the fault again. I will just delete it. Look, here is it's according to the global coordinate direction or global coordinate system. So it will be YZ and XZ. So once I have it, I will cut it. It's my first plane, and this is my second second plane. So I will just save it, and we can move forward because uh, we have selected, or sorry, we have just partitioned um, the model into the four pieces. So actually, I will come back to the concrete, and I will create the sets. So at first, the set all. So I will just select all. So and actually the surfaces, I will write surface inner, and I will create for my contact. If you just hold the shift tab, you are able to select. Yeah, I will select those faces. Perfect. And actually for boundary condition, once I will just rotate it, change the isometry, yeah, like that. So I will create a set that is called BC. It will be like a boundary condition. So actually I can just select everything except the top surface, and I will confirm. Um, in the same manner, I will create the rebar set where will be all. Perfect. And the surface, it will be surface outer. Or I can type outer, yeah, like that. I will confirm. And yeah, look, I just made a little bit mistake, so I can just edit it. Okay, confirm, and actually right now it's according to my expectation. Uh, Amazing. So everything is set up from the point of view of the part. We can just move forward to material properties. At first, I will just define the concrete that will have some density 2.5 E minus 9, and the elasticity, the modulus of the elasticity is approximately 32,800 and Poisson ratio 0.25. The material will stay elastic, isotropic. We will not like put inside any nonlinearity into the concrete because that's not the goal. Um, Actually, once I will just submit it, I can just create another material that will be bar, where I will put a density 7.8 E minus 9, and the elasticity that will be used here is like 200,000 um, megapascal, and actually it will stay like that. Actually, right now I need to pair it together with this material properties. So once I have the rebar here, so I can just create a section. The section will have addressing this, or I will address the same name to have it unified. It's a solid. I will also use a bar, and actually right now I will just connect it with the rebar as the volume with the material. So actually, look, this is the reason why I just created this all properties or all set to select it and assign it. That's always good that you will just predefining sets. That's much faster to handle all the operations. Actually, the concrete, once the concrete will discover here, I will just call it concrete. It's a concrete, and I will assign it again, all assign, and you will select concrete. Once everything is properly assigned, the the volume will change the color. So that's great identification that you did it properly. Yeah, and this is the material properties. Yeah, so actually right now we can just move to assembly, where I will just define the instances first and the second, and do not forget to use the auto offset to have it visible. Actually, we wanted to have it like a mesh on the part, so leave it as a dependent. So once I have it, I need to just switch the parts coloring and to make it more obvious, and I need to put the bar inside. So actually, I will just use the move. At first, I will just take this point and relate it here. So once I have it, I need to just double check where is my contact, because there are some surfaces. The surface outer, as you can see, that's been created, so that's properly assigned. In the bottom there will be created also the contact, and we need that uh, for proper alignment with the inner surfaces to binding together the contact surfaces. Actually, that's correct. So we can again move the bar, but at first I need to select the axis or start point. I can just leave it at the position like that. And in the second step, I need to just move it in the Z direction about the 100 millimeters. So there will be like a 100 millimeters. Once you do it, you can just confirm, and to validate that everything is passing, I can just move forward like a inside and double check if my interface is passing and nothing is overlapping, or if some gap has been like diagnosed, you know. Okay, so we just finished up the assembly and we can move forward to the interaction. So actually in the interaction, I will just need to set up the reference point. The reference point will be aligned with the center point on the rebar. So actually to this reference point, I will just create a coupling that will like bind together this reference point with the surface. So I will just name it like a RP, um, RP. So I will just select it and select also the surface. The surface will be basically here, and the coupling, will be the kinematic. So actually, once the coupling has been assigned, so that's the kinematic, I would say, equations has been assigned, and we can basically move forward to definition of the contact. So at first, I need to create a property of the contact. So it's called contact, and once once I will just create it. I will create the mechanical normal behavior, and it will be hard contact in the normal direction to prevent the penetration. And actually in the cohesive behavior, there will be like just the slip that is representing the shear. I will specify the stiffness. The stiffness will be uncoupled, as I mentioned in the previous presentation. So there have been just the explanation about the coupled and the uncoupled system of the traction stiffnesses. Actually, at this point, I will set up 1.39 and 1.39. So that is a very good question. Where did I get this number come from? So it's basically coming from the stiffness that is calculated in between the maximum peak bone stress or the traction divided by the slip. So it's like a 2.5 divided 1.8, and the units are Newton per cubic millimeter. So actually, once I have it, I can just come back here and set up the damage. The damage in the normal direction, I will specify the damage evolution at first. The total displacement or total slash plastic displacement is 8.2 millimeters. What does it mean? If I come back to the presentation, so the total versus plastic displacement is always the total slip at the fracture minus the slip in the beginning of the damage initiation. So it's like a slip at the peak. Okay, so this is the 8.2 in our case. And actually, once I come back to the initiation, I need to just put here very small value for normal traction and 2.5 and 2.5 in one and the second direction. It's like a tangent direction and also the longitudinal direction on the rebar. So the criterion is quadratic traction. So I will just confirm that. Once I have it, I can just come back to the step where I will define the physics. The physics will be like a static general. Um, I will define the nonlinear geometrical linearities, I would say. There will be 100 increments, sorry, 100, yeah, maximum number of increments is 100, and the step increment size will be like 0.01. So there will be totally, I will stop at 1. So this is what I want. This is my setup. And actually, I will come back to the definition of the field output. So once I will go closer to editation, I would like to receive every increment, the results at the integration point. And what I will just select is the um, stress tensor of the stresses. This is what I want to see. I want to see the total strain, not plastic, because there won't be any. Um, from the point of view of the displacement, yeah, this is the translation and the rotation. Actually, reference reaction forces and the moments, contact stress. Contact stress, I wanted to see the contact status. And once I'm coming to failure fracture, it will be damage that I need to specify. This is the scalar stiffness degradation for cohesive surfaces and quadratic traction damage. This is the output what I want to see. Maybe I will find any uh, some like more outputs that can be relevant, but actually for this state that is for us interested in as a damage and I would say um, traction slip interaction or traction slip curve that I want to get it out of the simulation. So it's enough actually at this history output where I can track like every increment on the specific um, set. The set will be related to RP. It will be energy. It will be like a displacement in the Z direction, U free, and you will specify, or I can specify also the forces because the forces in the third or Z direction, not third, will be like that. So actually, in every increment, I wanted to follow this trend. Okay, perfect. I have it. And actually, once I come back to the interaction, what I forgot, I just assigned and created the interaction properties, but I didn't link it. So I will just utilize the initial step, and there is like a general contact. So I will also rename it as a contact. So once I have it, I can just move here and assign the global assignment. The global assignment is contact. Yeah, and actually it's been already defined. So once we have it, we can just move forward to loads. Yeah, we can just move forward to the loads. Actually, at this point, I will just create a boundary condition. The initial boundary condition will be on I would call it BC new. It will be on the faces. Okay, so it will be here, and to just click it over there. Okay, and in the bottom. Perfect. I will just confirm and select U1, U3, U2 because there is just a solid element that has just the translation and degrees of freedom. Actually, I need to just move to definition of the deformation. The total fracture displacement is 10 millimeters, so I will assign to the first step the load, and the load will be in the form of the displacement in the on the set that has been predefined as RP. It's in the third direction, 12 millimeters, in the positive direction Z, and the amplitude will be equally spaced with a 0 and 1 one amplitude. Yeah, actually right now that's the step is equally distributed load over the step. So here is the amplitude. Actually, here exists some plugin for amplitude plotter where you're able to plot it, and you will see that it's been utilized. It's been utilized like that. Um, so actually, we can just step by the mesh. I just already prepared the mesh. This is I would say uniform hex mesh with a reduced integration. Um, So it looks uh, it looks fine. Of course, always it can be refined, but this is not our goal. Our goal is to have like a output that are aligned with our um, expectation that is coming from the curve we just developed in the Python. So uh, this is it. Actually, right now I can just move forward to the jobs. I will just create a job and use the parallelization to utilize more processors, confirm, and I can just the submit. So we have completed the simulation. Once I will go to the results, I can observe some outputs that have been chosen. So at first place, I will check the deformation. So actually, deformation. Once I will go to the viewport and a little bit edit it, so there will be not the scientific but fixed, maximally 2 decimals. It's enough. So for yeah, that's good. Okay. So 12 millimeters is in the 100 by the 100 increment. And actually, I can just display and print the history output. It will be the force versus displacement in this Z direction. So once I will do that, I just plot it like that. You can see that I'm just coming to 15,000 Newton and dropping down to time approximately 0.83, so 83 increment, 83rd increment. And since this point on, there is like a zero stiffness. The damage is equal to, from this point on, is equal to 1. But actually, our solution that is here, if I just maximize the screen, I can see that here is traction shear, it's in the megapascal, and here is like a slip. So I would like to do it in the same way. Actually, once I come back here, I have those two data. This is not what I need actually right now. So I can just yeah, I can just delete it, and I need to convert the force to the shear, or to the traction in general, to the Newton per millimeter square. So I have like two options. The first option is that you can go to the shear and you can just, read out immediately what is happening with in the form of the shear. So once I will just create a cut, um, once I will create the cut, I can also like select just the concrete part. I can just go to the shear and I can select one of the elements. So once I will go to the field output, so it will be in the part of element nodal. It's a frictional shear stress. I will just select. Okay. So save as. I need to go to the average to have it just there, one curve, and I will plot it out. So you can see that it has reached approximately 2.5 megapascal, and descending down from this point of the damage initiation down. So actually, once you display the symbols, you can see how many iterations we reached. It's like 100 iterations. Um, so it looks like that. That's this is also the reason why here is like a missing point, and that peak or the spike is like a uh, cut it through, because we need to add like more to have it a spike to have like we need to add more increments. Okay, so but this is not what we want. We want to have like a stress dependent on the slip. So actually, I will come back here and I will just display everything, turn off this cut option, and actually, I will go to history output. In the history output, I will just select those two predefined sets. I can just print it, of course. It looks like that. You can see that's quite similar, but here's a force and here is the displacement also. So I need to combine together all those data. So at on the horizontal direct on the in the horizontal axis is U3, but I need to combine that. So here is a combine. My fault. Combine U3. If I will put a comma and put a reaction, divided by 6,283. So how I just received the number, if I will take a calculator and create that my diameter, here is a P, here is a P somewhere. Yeah, P times diameter is 20 and the embedded length is 100. So I have a 6,283 and this is my surface that is basically um, resisting. Yeah, the surface is resisting to the force, so you will receive the stress. So actually, once I will plot it, you can see that I will receive the same. But at my point here, if I will take a pen, so here is a 1.8, so this is my, I would say, peak, and from this point on, I'm just going down to 10 millimeters. Oh, I need to go to the 10 millimeters. It's here. Look. And from this point on, there is like a failure mode. I would say that the slip at the fracture is at the 10 millimeters, and the stiffness basically is equal to zero. So traction is equal also to zero here. So it works quite well actually. And right now we will just double check what is happening if you put the user-defined damage and the slip into the ABAQUS. So I just outlined the very brief results because in the next session we will go deeper to explanation of the results, how it works, and actually how the criterion been built up and many more. But actually at this phase, I will just come back to Python and introduce how the damage is calculated. Okay, so let's check what we have inside the Python script for user-defined bond. So actually, those are the inputs as a maximal peak or peak of the stress. I mean the traction at the damage initiation. This is the slip at the damage initiation, and this is the fracture slip S4 that is 10 millimeters. So once I want to calculate the stiffness, so here is like just a division for the longitudinal and the tangential shear. It's here. So once I will print it, so I will get the stiffness. Okay, so um, actually right now I'm just will be storing or appending the data to damage. So here is the condition if the slip is lower than basically slip at the initiation, the damage will be equal to zero. Once it will be start the damage initiation to the final or to the fracture slip, so will be used this damage calculation. So this equation has been elaborated and explained in the previous session. So if you haven't seen that, so just feel free to step in and watch it again. To reply that, here is also the traction. The traction is calculated based on the like a two intervals, I would say. The first is still till the damage initiation, and from this damage initiation will start or onset and will go on. So there will be used the damage that is calculated, or the traction that is based on the damage that has been calculated in the previous equation or for loop. So I want to know what is basically happening, and the best way how to understand is to display the graph. So I just created like a three separated graph, one for slip versus traction, slip versus damage, and traction versus damage. In the bottom part, there is like a storing of the slip damage data that I'm just will be using for total slash plastic displacement. Those are the data that will be used here. Actually, that's been stored in the text file. So I will just check that there is a damage is on the left side and total displacement is on the right side. So if I run it, I would be able to see that. So actually what happened here has been printed out the traction versus slip graph. Here is the damage. As you can see, the onset will start at the 1.8 and has some like a hyperbolic shape. And this is the traction versus damage. Again, that's like affine to this um, yeah, to this plane. Okay, once I will just finish it, as you can see, the console just give me the message the shear stiffness is equal to 1.39 Newton per cubic millimeter. And here is written, yeah, slip versus damage. So if I will just double click here. So the damage is equal to 0 and the slip is negative. Once the slip is negative, it means there is zero damage. So once the damage will occur, so there is like a first level of the slip. So this is my final value. I will just step in here. Okay. So the first damage here, I will put like a 0, and here displacement will be 0. And once I will just check it here, I don't know, I need to insert a row after. There will be like a 1 and 8.2. Okay, so this is how it should be working. Once I confirm that, I will just create another job. Call it linear user defined. So once I have it, I'll just put here parallelization, and I can submit the session. So perfect. So we just completed the simulation, and we'll expose the results. So the first result will be the standard curve. Yeah, I will just go up here to history output, and I will just plot it. So it looks good. It is also 15,000 Newton. So actually I will combine those two curves together, and here we'll combine. I will just U3 and put there the force divided by 6,283. So once I will do that, so as you can see, I'm just reaching 2.5. Here is like a 10 millimeters. So it's exactly the same as the curve, as the previous curve. So the damage has been assigned properly. And once I will do the elimination of the rebar, basically, so I will just eliminate or remove the rebar, and I will select, because I want to see the damage. So I will go to the ODB field output. So if I have ODB field output, there is like a unique nodal, and I can double check the scalar of the scalar stiffness. I will just select, for example, this element. Once I will save it as average because there is like 8 nodes. Okay, it's average, and I will plot it. So as you can see, the curve is represented in the same manner and same train. The traction looks the same as hyperbolic as in the previous I would say created curves from the Python. So we can say that it behaves according to our expectation. Um, so it looks good. So this is just the brief overview and the final message for this session, that the output looks reliable. Um, quite, I have fidelity that the results are matching each other, the inbuilt and also the user defined input. And in the next session, we will just talk more about the how to plot the results and also compare it with the curve from the Python. So actually, this is it for this session. So I do believe that you enjoyed that. So once just letting you know that if you enjoy the session, so don't hesitate and drop some message, or and please do not forget to subscribe this channel for more valuable content. Apology. Thank you and have a nice day.